Welcome to Sleepy Science Universe. Tonight, there's a quiet detail you can hold without effort. Starlight is a soft kind of time travel. The glow that reaches your eyes has been on the way for years or centuries or far longer, and the newest stars are often being born behind curtains of dust that normal eyes can't see through. As we drift through these gentle facts, you may start to notice how star birth is slow, layered and surprisingly calm. Before we begin, take one easy breath in through your nose and let it out slowly in your own time. No need to do it perfectly. If this style of quiet science feels like a good place to rest, you're welcome to settle in with it. And you can subscribe or return again whenever it feels natural. Now, let's begin with one clear fact about what a star is. A star is a sphere of hot gas that shines because it makes its own light. Gravity pulls gas inward until the center becomes hot and squeezed enough for atoms to fuse, releasing energy that becomes light and heat. The Sun is about 1.4 million kilometers across, which is roughly 109 Earths lined up side by side. Plasma is the main state of matter inside stars. Plasma is a gas heated so much that its electrons aren't bound tightly anymore, so the whole thing can carry electric currents. The Sun's surface is about 5,800 Kelvin, which is around 5,500 degrees Celsius, and that's one reason its light feels so steady and clear. And for one sleepy soul, that's enough to rest. Gravity is what holds a star together against its own heat. A star is always balancing inward pull and outward pressure, like a slow, quiet tug of war that never needs to rush. The Sun's mass is about 2 × 10 to the power of 30 kilograms, around 330,000 Earths, all held together by that patient inward pull. The Sun is a medium star, not a giant one. Many stars are much smaller and dimmer than the Sun, and many are far larger, even if they're much farther away. A typical red dwarf can be about 10% the Sun's mass, like a smaller, cooler ember compared to a steady candle. In the background, red dwarfs are the most common stars in our galaxy. They burn their fuel so slowly that they can keep shining for an almost unimaginable span of time. Some red dwarfs may live for trillions of years, far longer than the Sun's total life. Blue, massive stars shine brighter because they burn older and all faster. More mass means stronger gravity, and stronger gravity squeezes the core harder, raising temperature and speeding up fusion. Some very massive stars live only a few million years, as if they spend their fuel in a bright, brief rush. Luminosity is how much total energy a star emits each second. A star can be truly powerful but still look faint if it's very far away, and that's why distance matters so much in the sky. The Sun's luminosity is about 3.8 × 10 to the power of 26 watts, a number so large it mostly just means enormous and steady. And for one sleepy soul, that's enough to rest. A light year is a distance, not a time. It's how far light travels in 1 year as it moves through space at its constant speed. 1 light year is about 9.46 trillion kilometers, which is a distance big enough to make even our solar system feel like a small room. Starlight arriving tonight left its star long ago. Distance turns the night sky into a gentle archive of the past, because you can only see a star as it was when its light began the journey. Polaris is roughly 430 light-years away, meaning that the light you see has been travelling since long before modern life as we know it. A constellation is a pattern from our viewpoint, not a physical group. The stars that make a familiar shape can be at very different distances from us, separated by huge stretches of space, even if they look close together. Within one constellation, distances can differ by hundreds of light years, like distant lanterns lining up by chance. A small step forward, a star's colour tells you something about its surface temperature. Hotter stars peak in bluer light, while cooler stars peak in redder light, even when the difference looks subtle to the eye. Blue stars can exceed 20,000 Kelvin at the surface, while cooler red stars may sit below 3,500 Kelvin. The Hertzsprung-Russell diagram is a map of star brightness versus temperature. It's a simple idea. Plot how hot a star is against how bright it truly is, and patterns appear that tell the story of stellar lives. The main sequence on that diagram spans many orders of magnitude in luminosity, meaning stars can differ by factors of thousands, millions, or more in power. The main sequence is where stars spend most of their lives. It's the long, stable phase where hydrogen fusion in the core provides a steady source of energy. The Sun's main sequence lifetime is about 10 billion years in total, a calm, slow burn measured in deep time. And for one sleepy soul, that's enough to rest. The Sun's about halfway through its main sequence lifetime. It has been shining for about 4.6 billion years and has roughly 5 billion years left in this steady phase. In the scale of stars, that's a quiet middle age, with no need for urgency. A giant star is giant, mostly in size, not always in mass. Some stars swell outward when their internal structure changes, becoming huge but with a cooler surface. Red giants can reach tens to hundreds of times the Sun's radius, like a familiar light suddenly filling much more space. Betelgeuse is a famous red supergiant near the end of its life. It's enormous and variable, and it helps astronomers understand what late stellar stages can look like. Estimates vary, but its radius is on the order of hundreds of sun radii, so wide that if it replaced our Sun, it would reach far past the inner planets. A softer detail, white dwarfs are the compact leftovers of Sun-like stars. They no longer fuse in their cores, but they glow from stored heat slowly cooling over time. A white dwarf is about Earth-sized, yet can hold a mass similar to the Sun, which is a gentle reminder of how gravity can compress matter. Neutron stars pack extraordinary mass into a tiny space. They are the collapse cores of massive stars, squeezed until matter is almost entirely neutrons. A typical neutron star is about 20 kilometers across, city-sized, yet it can contain more mass than the Sun. Black holes can form when very massive stars collapse. If the remaining core is heavy enough, collapse can continue beyond the neutron star stage. For a black hole with a few solar masses, the event horizon can be only tens of kilometers across, which is small compared to what the star once was, and for one sleepy soul that's enough to rest. Most stars are born in groups, not alone. Big clouds of gas and dust tend to break into many collapsing pockets, creating clusters of young stars. A single stellar nursery can form hundreds to thousands of stars like a soft scatter of lights that slowly spreads out with time. Our Sun likely formed in a stellar nursery with many siblings. Over millions of years, that birth cluster would have dispersed, and these siblings would have drifted into different orbits around the Milky Way. Many clusters disperse in tens to hundreds of millions of years, which is slow enough to feel gentle, but fast compared to the age of the galaxy. Star birth begins in cold, dark molecular clouds. These are regions where hydrogen is mostly in a molecule form, and where dust blocks visible light, hiding what's happening inside. Typical temperatures can be around 10 to 20 Kelvin, so cold that even a small amount of warmth is meaningful. Just for a moment, parallax is a star's tiny shift in position as Earth orbits the Sun. As we move from one side of Earth's orbit to the other, nearby stars appear to shift slightly against the more distant background. A parallax of 1 arcsecond corresponds to 1 parsec, which is about 3.26 light years, and it's one of the calm geometric ways we measure space. A parsec is another distance unit astronomers use. It's built directly from parallax, so it fits naturally into measurements of the sky. 1 parsec is about 3.26 light years, which is roughly 31 trillion kilometers, though the number is less important than the sense of scale. Apparent magnitude is how bright a star looks from Earth. It combines the star's true brightness with its distance, and also with how much dust dims its light along the way. A difference of 5 magnitudes equals a factor of 100 in brightness, so the scale is steep even when the numbers feel small. Here's a calm surprise. Absolute magnitude is how bright a star would look at a standard distance. The point is to compare stars fairly, as if they were all placed at the same range from us. That standard distance is 10 parsecs, about 32.6 light years, like moving every star onto the same quiet stage. Interstellar dust can dim and redden starlight. Dust scatters and absorbs blue light more strongly, so what remains can look warmer and redder. In dense regions, dust can hide stars by many magnitudes, as if someone gently pulled a dark veil across the sky. Infrared telescopes can see into dusty star nurseries. Infrared light has longer wavelengths than visible light, and those longer waves can slip through dust more easily. This is why places that look dark to our eyes can glow with hidden detail when seen in infrared. And for one sleepy soul, that's enough to rest. Spectroscopy splits starlight into colours to reveal what stars are made of. When you spread the light out, you see dark and bright lines that act like fingerprints for different elements. Hydrogen's strong visible line at about 656 nanometers, called H-alpha, shows up often in star-forming regions and hot gas. Stellar spectra can also reveal a star's temperature. Hotter objects have sectra that peak at shorter wavelengths, and cooler objects peak at longer wavelengths, which is the same basic idea behind colour and heat. You don't need the formula to feel it. It's simply that stars leave clues in their light. The Doppler effect lets astronomers measure a star's motion toward or away from us. If a star is moving away, its spectral lines shift slightly toward red. If it's moving toward us, they shift toward blue. In our neighbourhood, these motions are often measured in kilometers per second, which sounds fast, but is still part of the slow dance of the galaxy. Almost without effort, binary stars let us measure stellar masses. When 2 stars orbit each other, gravity sets the rhythm, and that rhythm reveals how much mass is involved. Many stars are in binary systems, and among massive stars the fraction in multiples can be especially high, often estimated above half. Eclipsing binaries dim in a predictable rhythm. From our viewpoint, one star passes in front of the other, causing a gentle dip in brightness, like a slow blink. Their periods can range from hours to years depending on how close the stars are and how quickly they orbit. Star clusters are useful because their stars share an age and distance. That means differences between the stars are often due to mass and internal physics, not because they are all at different stages of the universe. The Pleiades cluster is around 100 million years old, young on a cosmic scale, like a bright spark in the Milky Way's long night. And for one sleepy soul, that's enough to rest. Open clusters slowly spread out over time, gentle gravitational nudges, passing clouds, and the galaxy's tides gradually loosen them until the stars become part of the wider background. Many open clusters dissolve within about 100 to 500 million years, leaving only the memory of their shared origin in their motions and chemistry. Globular clusters are ancient, dense swarms of stars. They orbit galaxies and can contain some of the oldest known stars, packed together like a quiet sphere of starlight. Their ages are often around 10 to 13 billion years, so they carry a whisper of the early universe. Variable stars change brightness for physical reasons, not just because of clouds or distance. Some stars pulse, expanding and contracting in a steady rhythm as their outer layers respond to changes in pressure. Cepheid variables, for example, often have periods of days to weeks, like a slow heartbeat of light. In the slow distance, Cepheid variables help measure distances across galaxies. Their pulsation period is linked to their true brightness, so if you measure the period and the apparent brightness, you can infer distance. With good telescopes, they can be used out to millions of light years, helping us map the nearby universe. Supernovae of a certain type can serve as even brighter standard candles. Because their peak brightness is similar from one event to the next, they can be seen across enormous distances. Some can be observed across billions of light years, which means they become markers that reach far beyond our own galaxy. A star's proper motion is its slow drift across the sky. Nearby stars can shift noticeably over years and decades when measured carefully, like a slow slide against the background. Barnard's star moves about 10 arcseconds per year, which is fast in astronomical terms, and still incredibly gentle in human terms, still and steady. The nearest star system to the Sun is Alpha Centauri. It's a small system with multiple stars, including the red dwarf Proxima Centauri, which is the closest of all. The distance is about 4.24 light-years, so even our nearest neighbours are still separated by a quiet ocean of space. Light from the Sun reaches Earth in about 8 minutes. That means even sunlight is already a little bit in the past when it warms your day. The travel time is about 8 minutes and 20 seconds, a small number that still carries the feeling of distance when you sit with it, and for one sleepy soul, that's enough to rest. A star's life is mostly controlled by its mass. The amount of mass sets the pressure in the core, and that pressure sets the temperature, and the temperature decides how quickly fusion can run. As a simple rule of thumb, lifetimes fall steeply as mass rises, which is why a heavy star can blaze briefly, while a small star can last far longer than the current age of the universe. In the slow distance, astronomers call everything heavier than helium metals. It sounds strange at first, but it's just shorthand: carbon, oxygen, silicon, iron. Anything beyond helium counts as metal in this context. In the Sun, these heavier elements are only a few % of the mass, yet they matter deeply for how clouds cool and how planets form. Metallicity affects how easily clouds cool and fragment into stars. Heavy elements and dust grains help a cloud radiate heat away, and a cooler cloud is more willing to collapse. In dense regions, temperatures can drop toward about 10 Kelvin, cold enough that gravity can work with less resistance. And for one sleepy soul, that's enough to rest. The Milky Way is a rotating disk galaxy with spiral arms. Those arms are places where gas and dust tend to gather, and where the raw material for new stars is often thickest. The Milky Way is roughly 100,000 light-years across, which is a width so large that it turns across the galaxy into a phrase of true distance. The Sun orbits the Milky Way's centre like a slow carousel. Our entire solar system travels through the galaxy together, carrying us around in a path we only notice through careful measurement. One full orbit takes about 225 to 250 million years, so a single galactic year is long enough to hold entire ages of life on Earth. Spiral arms are not rigid arms, but waves of denser material. As gas moves through these denser regions, it compresses, and that compression can encourage star formation in the same way a gentle squeeze can encourage a cloud to gather. The density can rise by factors of a few, and in space even a few can make the difference between drifting and collapsing. Around the edges, emission nebulae glow when hot young stars energize surrounding gas. Ultraviolet light knocks electrons away from atoms, and when electrons recombine, the gas emits light in specific colours. Hydrogen's H-alpha glow at about 656 nanometers is a common signature, and it's one of the reasons some star-forming regions appear softly reddish in photographs. Reflection nebulae shine by scattering nearby starlight. They don't generate light the way a star does, they simply borrow and redirect it. Dust grains can be micron-sized, tiny like smoke, yet spread across such large spaces that they can paint whole regions of sky with a faint haze. And for one sleepy soul, that's enough to rest. Dark nebulae look empty, but they're often full of cold dust and gas. They block visible light like a curtain, hiding what's behind them and what's happening inside. In dense places, dust can dim starlight by many magnitudes, which is another way of saying it can turn a bright background into quiet darkness. Starbirth is easiest where gas is dense, cold, and gently compressed. A cloud needs to lose heat to keep collapsing because warmth acts like pressure pushing outward. Dense cores can reach around 10 to the power of 4 to 10 to the power of 6 particles per cubic centimetre, still thinner than any vacuum you'd make on Earth, and yet dense enough in space to begin a new star's slow beginning. A small step forward now and then, it can be comforting to pause and let the sky become a background again. Take one slow breath in through your nose, easy and unforced, and let it out as if you're fogging a window. Long, soft, and quiet. You don't need to keep track of every fact, because these are the kinds of ideas that can simply drift by, like distant lights seen through a train window at night. We've been moving through a simple chain. Dust can dim and redden light, infrared can see through dust, and measurements like parallax and spectra let us understand what we can't touch. And beneath it all is the calm requirement for starbirth, a pocket of gas that can cool, grow dense, and let gravity do its patient work. If your attention wanders for a while, that's perfectly fine. Let the details blur into a soft, starry hum, and return only when something gently catches your curiosity. A softer detail, fusion, is when light atoms combine and release energy. In the cores of stars, hydrogen nuclei join in steps, and a little bit of mass turns into energy that becomes heat and light. The idea is captured in the simple relationship E equals mc squared, which just means that even a tiny amount of mass can correspond to an enormous amount of energy. The Sun primarily fuses hydrogen into helium through the proton-proton chain. It's a slow sequence that works well at the Sun's core conditions, and slow is part of why the Sun can shine steadily for so long. The core temperature is about 15 million Kelvin, and in that deep heat, fusion can proceed without needing any sudden bursts. And for one sleepy soul, that's enough to rest. Stars shine for so long because fusion in their cores is steady, not explosive. If the core heats up a little, pressure rises, the core expands slightly, and the temperature eases back down, a kind of built-in thermostat. As a rough figure, the Sun converts about 600 million tons of hydrogen into helium each second, and even that enormous number is small compared with the Sun's total supply. Radiation is one way energy moves outward inside stars. Photons created in the core don't stream straight out, they bounce, scatter, and change direction countless times, like a slow wander through an endless maze. That random walk can take thousands to hundreds of thousands of years, depending on how you estimate the journey from core to surface. Closer in, convection is another way energy moves, like slow boiling. Hot material rises, cool material sinks, and the motion carries heat outward through bulk flow. In the Sun, the convection zone covers roughly the outer 30% of its radius, a vast region of rolling motion hidden beneath a surface that looks calm from far away. The Sun's visible surface is called the photosphere, It's the layer from which most of the light we see escapes into space, even though the Sun has no solid ground in the usual sense. The photosphere is only about 500 kilometers thick, which is astonishingly thin compared to a radius of about 700,000 kilometers. For one sleepy soul, that's enough to rest. Sunspots are cooler regions caused by magnetic fields. Strong magnetic structures can inhibit convection, reducing the flow of heat to the surface in those patches. Sunspots can be around 4,000 Kelvin, compared with roughly 5,800 Kelvin around them. And that difference makes them appear dark by contrast, not because they are truly cold. The Sun's magnetic activity follows a cycle. The number of sunspots tends to rise and fall in a slow rhythm, along with other forms of activity. That cycle is about 11 years, a gentle pulse of change that repeats without hurry. The chromosphere sits above the photosphere and glows in specific colours. It's thinner and hotter than the photosphere, and it shows strong emission in lines such as hydrogen's H-alpha. Temperatures can climb toward about 10,000 Kelvin in parts of this layer, even though it's farther from the core, one of those quiet reminders that atmospheres can behave in surprising ways. In a different light, the corona is the Sun's outer atmosphere, surprisingly hot. It can reach around 1 to 3 million Kelvin, and the details of how it stays so hot involve magnetic fields doing complex work. The corona is faint in visible light, which is why it becomes most obvious during an eclipse, when the bright disk is hidden and the halo can finally be seen. And for one sleepy soul, that's enough to rest. The solar wind is a stream of particles flowing outward from the Sun. It carries a magnetic field with it and fills the solar system with a thin moving plasma. Typical speeds are around 400 kilometers per second, and sometimes higher, which sounds fast, yet it's part of an ongoing quiet outflow that never really stops. Helioseismology uses sun vibrations to study the interior. The surface of the Sun ripples in many modes at once, and by measuring those ripples, scientists infer the structure of hidden layers. Many oscillation periods are on the scale of minutes, like a complex chord being played very softly over and over. Astroseismology does the same kind of listening for other stars. Tiny changes in a star's brightness can reveal its size, its internal layering, and clues about its age. The variations can be as small as parts per million, so subtle that they feel like listening for a whisper in a wide field. As night holds still, neutrinos are tiny particles made in fusion that pass through matter easily. They escape from the core quickly compared to photons because they barely interact with anything along the way. In an order of magnitude sense, billions pass through your body each second and you never feel them, which is a strangely gentle thought, something so constant and so unnoticed. And for one sleepy soul, that's enough to rest. Hydrostatic equilibrium is the balance that keeps a star stable. Gravity pulls inward and pressure pushes outward, and the near balance between them allows a star to hold its shape for a very long time. For sun-like stars, that stability can persist across billions of years, a kind of slow steadiness that is almost hard to imagine. A star's core grows hotter over time as hydrogen runs low. With less hydrogen available in the core, the structure shifts, and gravity compresses the center a bit more, raising temperature. As a rough trend, the Sun's brightness increases by about 10% per billion years, a slow change that only matters on the scale of geology and evolution. The CNO cycle is another hydrogen fusion pathway used by hotter massive stars. In this cycle, carbon, nitrogen, and oxygen act as helpers that speed the fusion process, even though they are not consumed in the net result. It tends to dominate when cores are hotter, around the high tens of millions of Kelvin, with a common threshold estimate near 17 million Kelvin. From the inside out, opacity is how strongly stellar material blocks light. Higher opacity means photons are more easily absorbed or scattered, slowing the outward flow of radiant energy. Opacity changes with temperature and composition, which is one reason star interiors can behave differently even when they share the same basic physics. Pressure in stars comes from both hot gas and radiation. In very massive stars, radiation pressure becomes especially significant, because intense heat means intense photon energy pushing outward. Radiation pressure scales strongly with temperature, often described as growing with temperature to the fourth power, which makes heat a powerful player in giant stars. And for one sleepy soul, that's enough to rest. Massive stars can lose material through strong stellar winds. Their intense light and high temperatures help drive gas away from their surfaces, shedding mass over time. Wind speeds can reach thousands of kilometers per second, and the escaping material helps enrich the space around them. Rotation can shape a star's behavior and its magnetic fields. Spinning stirs interiors and helps power dynamo processes that create magnetism. Some stars rotate in hours, while the Sun rotates in about 25 days at its equator, a slow spin compared with many of its younger, more active cousins. Stellar flares are sudden magnetic releases on active stars. Magnetic fields can twist and store energy, and when they reconnect, a star can brighten briefly in a sharp, clean burst. Many flares last minutes to hours, a quick shimmer against a much longer life. Sometimes it's enough to know that even a flare is just magnetism relaxing back into a quieter shape, and for one sleepy soul, that's enough to rest. The Sun's energy output is remarkably stable day to day. Even with spots and flares, the total brightness changes only a little, because the Sun is so large and its steady fusion dominates the average. Across the full activity cycle, total solar irradiance varies by roughly about 0.1%, a small swing for such a powerful star. Fusion in a star's core depends on quantum tunneling. Even when protons would normally repel each other, quantum rules give them a tiny chance to slip close enough to fuse, and in a star's crowded core, those tiny chances happen countless times. The probabilities are small, but the number of particles is so enormous that small becomes steady. Helium fusion begins later in a star's life when cores get hotter. Helium nuclei can fuse into carbon once temperatures climb high enough, opening a new chapter of internal chemistry. A useful scale to remember is around 100 million Kelvin, an order of magnitude threshold that tells you just how much hotter later can become. A softer detail, carbon, oxygen, and heavier elements are forged in evolved stars. Stars are slow factories that build the ingredients for rocky worlds, grain by grain, fusion step by fusion step. Up to iron, many of the common elements can be made in stellar interiors and then returned to space through winds and explosions. In the long run, that quiet manufacturing is how galaxies become chemically rich. Iron marks a turning point because fusing it doesn't release energy. Up to iron, fusion can pay you back with energy, but beyond iron it becomes an energy cost, not a source. A simple anchor is iron 56 near the peak of binding energy, which is why iron sits at the edge of what a star can use as fuel. Pressure and temperature rise dramatically toward a star's center. A star is layered, and each deeper layer carries the weight of everything above it, like going down through an ocean of gas. For the Sun, the core density is on the order of about 150 grams per cubic centimeter, far denser than water, as despite being made of what started as diffuse gas. The outer layers of stars can ring and pulse in gentle rhythms. Some stars naturally oscillate because their layers expand and contract as opacity and pressure shift, like a slow, steady breathing you can measure. Periods can range from hours to months depending on the type of star, and those rhythms become clues to the star's hidden interior. And for one sleepy soul, that's enough to rest. The quiet physics of stars is mostly slow change measured over long time. We can't watch a single star live its whole life, so we compare many stars at different stages, as if we're piecing together a story from many still photographs. The contrast is simple. Human lifetimes are decades, while many stellar lifetimes are billions of years, which turns patience into a scientific tool. A molecular cloud can collapse when gravity overcomes internal pressure. Cooling helps because cooler gas pushes outward less, letting gravity tighten its gentle grip. Typical molecular cloud temperature can be around 10 Kelvin, and in dense cores the collapse times can be on the order of 100,000 years or more, which is slow enough to feel like stillness. The gene's mass is a rough threshold for when a cloud fragment can collapse. It compares the cloud's tendency to fall inward against its tendency to puff outward from heat, and it changes with temperature and density. A simple way to hold it is that if a cloud becomes colder by about half, the threshold for collapse can drop a great deal, making star birth more likely in that pocket. Just for a moment, clouds fragment into cores, and cores become individual forming stars. A large cloud can break into many smaller knots, each one a place where gravity slowly wins. Dense core sizes can be around 1/10 of a parsec in scale, order of magnitude, so they are small compared with a giant cloud, but still vast compared with anything on Earth. A protostar is a forming star that's still gathering mass. It shines mainly because gas is falling inward and heating up, not because full hydrogen fusion is already steady in its core. The protostar stage can last from about 100,000 years to a few million years, depending on how much mass is being assembled. There's something quietly reassuring about that. Even a star takes its time to become itself. Accretion is the slow feeding of gas onto a protostar. Material spirals inward, and as it falls it releases gravitational energy as heat and light, like a slow warming from within. Accretion rates can be around 10 to the power of -6 to 10 to the power of -5 solar masses per year, in many cases, a tiny fraction of a sun each year, and yet enough to build a star over time. Protostars often form with disks because the original cloud was rotating. Rotation makes infalling material spread into a flattened disk, because it can't drop straight in without shedding angular momentum. Disks can span tens to hundreds of astronomical units, meaning they can be larger than the orbit of Pluto, even while the forming star itself is still compact at the centre. And for one sleepy soul, that's enough to rest. Jets can shoot out from young stars along their rotation axis. Magnetic fields can help focus some material into narrow streams that escape instead of falling in. In some cases, jet structures extend for light years, carving faint lines through the surrounding cloud. Herbig-Haro objects are glowing shock regions made by these jets. When fast streams slam into nearby gas, the collision heats and excites the material, creating small luminous knots. Shock speeds can be on the order of hundreds of kilometers per second, which sounds fast, but still happens in the quiet, cold emptiness of space. Star-forming regions can be triggered by pressure from nearby massive stars. Radiation and winds from hot stars can compress nearby clouds, making certain edges dense enough to collapse. An H2 region can expand over thousands to millions of years, so the trigger is more like a slow push than a sudden shove. Farther out, an H2 region is a bubble of ionized hydrogen around hot young stars. Ultraviolet light strips electrons from hydrogen atoms, and when electrons recombine, the gas glows in characteristic colors. These bubbles can be tens of light years across, large enough to hold entire clusters inside them. The Orion Nebula is one of the nearest big star nurseries. It's close enough that telescopes can pick out young stars, disks, and streams of gas in rich detail. The distance is about 1,300 to 1,400 light-years, so what you see is a glimpse of a region as it was over 1,000 years ago, still busy in its hidden way. Dark pillars in nebulae form when dense gas resists erosion by radiation. Bright light and winds eat away softer material, leaving thicker columns behind with faint bright rims where radiation bites at the edges. Pillars can be several light-years long, like slow sculptures in a drifting fog. A Bock globule is a small dark cloud where a star may be forming. These compact pockets are dense enough to block background light, making them look like black beads against glowing nebulae. Many are around a light-year across or less, which is small by astronomical standards and still unimaginably wide by human ones. And for one sleepy soul, that's enough to rest. Young stars are often classified by how their light looks in infrared. The more dust and envelope material around a young star, the more the infrared signature changes, offering a gentle way to estimate stage. The Class 0 to Class 3 sequence spans a few million years in rough terms, moving from deeply embedded to mostly cleared and exposed. A T Tauri star is a young sun-like star, still settling down. It can be active and variable, with a disk that may still be feeding it in small amounts. Typical ages are under about 10 million years, which is young enough that planets may still be assembling nearby. Protostars heat their surroundings, changing nearby chemistry. Warmth can liberate molecules from dust grains and drive reactions that are rare in colder conditions, slowly reshaping what the cloud is made of. Snow lines shift with temperature, often tens to hundreds of Kelvin in scale, marking where different compounds can freeze and stick to grains. Sometimes chemistry in space is just temperature drawing invisible boundaries. Closer in, disks can show gaps and rings, hinting that planets may be forming. A forming planet can carve a path in dust, creating patterns that look like grooves in a record. The ring scales are often tens of astronomical units, big enough that a single ring could swallow the size of our entire inner solar system. ALMA has imaged detailed disk structures in nearby star-forming regions. It observes at millimeter wavelengths, which are well suited to tracing cold dust that glows faintly at these long wavelengths. Millimeter light simply means light with wavelengths about the size of a grain of rice, and it's perfect for seeing where cold dust is gathering. Brown dwarfs are failed stars that never sustained hydrogen fusion like the Sun. They form similarly to stars, but end up too low in mass to keep core hydrogen fusion running steadily. A useful threshold is about 0.075 solar masses, meaning less than roughly 8% of the Sun's mass. They glow faintly as they cool like embers that never become full flames. Deuterium fusion can happen in some brown dwarfs early on. Deuterium is a heavier form of hydrogen that fuses more easily than ordinary hydrogen, so some brown dwarfs can burn it briefly while young. The often quoted threshold is around 13 Jupiter masses, which is why that number appears so often in discussions of where planets end and brown dwarfs begin. And for one sleepy soul, that's enough to rest. Protostellar outflows help remove excess angular momentum. If all the rotation stayed in the infalling gas, it would be harder for material to settle into a compact star, so outflows help carry spin away. Outflow speeds can be tens to hundreds of kilometers per second, a steady stream that keeps the system from spinning too tight. Magnetic fields thread through star-forming clouds. They can guide collapse, shape disks, and help launch jets, even though the fields themselves are invisible to our eyes. In everyday units, these fields can be extremely weak, yet over huge distances they still steer charged particles and influence the flow. turbulence in clouds can both slow and seed star formation. Random motion can resist global collapse by stirring and supporting the cloud, and at the same time it can create denser pockets where gas piles up. In cold gas, the turbulence can be supersonic, which simply means it moves faster than sound would travel through that cold medium, creating shocks and compressions. Shock waves from older supernovae can compress gas and spark new stars. A passing shell can squeeze a cloud like a slow hand pressing foam, raising density in some regions and tipping them toward collapse. Supernova remnants expand over thousands to tens of thousands of years, so the trigger itself can be a long, slow approach. If you drift a little, some meteorites suggest the early solar system had nearby massive star influence. Certain short-lived isotopes in meteorites hint that a star ended explosively not too long before, or during, the solar system's formation, sprinkling fresh material into the locale. The timescales are short by cosmic standards, less than a few million years for some isotopes, which is why the clue feels so specific. A protostar becomes a true star when stable hydrogen fusion begins in the core. That switch on is gradual, more like settling into a steady lamp than lighting a match. For sun-like stars, the full path from collapsing core to stable main sequence star can take tens of millions of years, with a long youth before a long adulthood. Young stars can be surrounded by protoplanetary disks made of gas and dust. Dust grains stick and grow, slowly turning from tiny specks into larger aggregates that can become the seeds of planets. A simple comparison is grain growth from microns to millimeters early on, like dust turning into tiny pebbles in the dark. The snow line is where certain gases freeze into solid ice in the disk. Beyond a snow line, more solid material is available because ices add mass to grains and help them stick. In sun-like systems, the water snow line is often a few astronomical units out, though it can shift depending on the star's brightness and the disk's structure, and for one sleepy soul, that's enough to rest. Radiation from young stars can slowly evaporate disks from the inside out. High-energy light heats gas in the disk, and if that gas becomes energetic enough, it can escape, thinning the disk over time. Disk lifetimes are often around 1 to 10 million years, which means planet building happens in a limited window but still a very long one on human terms. Star formation is inefficient. Most cloud mass never becomes stars. Winds, jets and radiation blow much of the gas back into space, and only a small fraction ends up locked inside starlight. In giant clouds, efficiency can be only a few %, which means most of the cloud remains a drifting recycled reservoir. The initial mass function describes how many stars form at different masses. Nature tends to produce many more low-mass stars than high-mass stars, so the galaxy ends up filled with faint red dwarfs, and only a few rare giants. The simplest comparison is just that massive stars are rare compared with red dwarfs, even though the massive ones can dominate a region's light. Massive stars can sculpt their birth clouds quickly with intense ultraviolet light. Their radiation carves cavities, drives shocks, and can trigger new collapses along the edges of bubbles. Their lifetimes are short, often around 3 to 10 million years, so they reshape their environment fast compared with the calm billions of years of smaller stars. In a way, they hurry, and then they're gone. Under a wide sky, star birth is the story of slow collapse, brief youth, and then long, steady shining. The dramatic nebula phase that looks so vivid in images is short compared with the star's stable main sequence phase. A nursery can last millions of years, while a sun-like star can shine for billions, meaning the long middle of stellar life is the quietest part. Now and then it helps to let the story settle into a softer rhythm again. Take one easy breath in and let it go slowly as if you're letting a thought drift past without needing to catch it. We've been moving from the inside of stars out to the clouds that make them. Balance and fusion, then dust and collapse, then disks and slow, patient assembly. If you missed a detail, let it pass like distant light. The shape of the idea is enough. Cold gas gathers, gravity tightens, a protostar glows, a disk forms, jets and winds shape the scene, and at last a steady star begins to shine. You don't have to hold every piece. It's fine if the facts become a soft background, like a quiet sky you don't need to name in order to feel. And for one sleepy soul, that's enough to rest. Protoplanetary disks are mostly gas, with a small but crucial fraction of dust. The gas is the main mass of the disk, but the dust is the part that can become rocks, and then worlds, and then all the solid structure we recognize. A useful scale is that a disk might hold around 1% to 10% of the star's mass, which is plenty of raw material when the star itself is so large. For a moment you can imagine that thin disk as a quiet workshop, wide and dim, doing patient work in the dark. Gently speaking, dust grains can stick together through gentle collision in a disk. At first they are so small they behave like smoke, but tiny forces, electrostatic attraction, and sometimes sticky icy coatings let them clump. The growth is often described as microns to millimeters to centimeters, which is a simple ladder. Dust becomes grit, grit becomes pebbles, and pebbles become the next stage. Planetesimals are the first big seed bodies on the road to planets. Once objects become kilometers across, their gravity begins to matter, and growth can speed up because gravity helps them collect more material. A planetesimal is still small compared to a planet, but it's enormous compared to a dust grain, like the difference between a pebble and a mountain. Disk temperatures fall with distance from the star. Close in, the disk can be hot, hundreds to thousands of Kelvin, while farther out it can be only tens of Kelvin, cold enough for many gases to freeze. That temperature gradient quietly decides what materials exist as solids in different places, and solids are what build rocky cores. In a way, a disk is a gentle map where heat draws invisible borders, and for one sleepy soul, that's enough to rest. Hot Jupiters show that giant planets can end up very close to their stars. Many likely formed farther out where ices were abundant, then migrated inward through interactions with the gas disk. Some have orbital periods of only a few days, which means a year on that world passes in the time it takes you to settle into a new week. Some young stars show inner holes where the disk has cleared. The central region can be emptied by forming planets, by winds, or by the star's radiation slowly lifting gas away. These holes are often a few astronomical units in radius, a space comparable to the inner solar system, carved out inside a much larger ring. Disks can warp or tilt if a young star has a companion. A second star's gravity can twist the disk over time, bending it into a shape that is no longer flat. Binary separations range from a few astronomical units to thousands of astronomical units, so some companions are close enough to reshape a disk strongly, while others only whisper at the edges. Sometimes even a gentle gravitational neighbour changes the whole geometry of a newborn system. A quiet fact: stellar companions can limit how large stable planetary orbits can be. In some binaries, planets must orbit close to one star to stay stable, or they must orbit both stars at once in a wider circumbinary path. The boundary depends on the separation of masses, but the calm idea is that gravity sets safe lanes, where orbits can remain steady for long stretches of time. Young stars often spin faster than older stars. Over time, stellar winds and magnetic braking can carry away angular momentum, slowing the rotation like a top gradually easing down. Some young stars can rotate in less than a day, which means their surfaces whirl around with a quickness the Sun does not have anymore. Magnetospheres can funnel disk gas onto young stars in streams. Magnetic fields can guide charged material so it falls along curved paths, landing near the star's poles and creating hotspots. Those hotspots can rotate in and out of view over days, making a gentle rhythm in the star's brightness that comes from geometry and magnetism rather than from fusion changing. And for one sleepy soul, that's enough to rest. Stellar radiation can change disk chemistry by breaking molecules apart. Ultraviolet light carries enough energy to split some molecules, and the fragments can recombine in new ways, building different compounds. It's a slow chemical weather inside the disk, shaped by light and temperature. Ices in disks can trap gases and deliver them later to forming planets. In the cold outer disk, molecules can freeze onto dust grains, and those icy grains act like tiny storage boxes drifting through the dark. Carbon monoxide can freeze near about 20 Kelvin, an anchor point that reminds you how cold outer disk can be. Pebble accretion is a proposed way planets may grow efficiently. In this picture, small pebbles drift inward through the gas and can be captured by a growing core, feeding it steadily. Drift times can range from thousands to millions of years depending on conditions, which is still quick compared with a star's life and slow compared with ours. It's growth by quiet snowfall, rather than by dramatic collisions. Closer in, the habitable zone is the region where temperatures could allow liquid water on a rocky planet. It depends on the star's brightness, because brighter stars push the comfortable temperature band farther out. For the Sun, a rough estimate often quoted is around 0.95 to 1.7 astronomical units, though the exact edges depend on atmosphere and models, and the key idea is simply that stars set a temperature landscape. Red dwarfs have close inhabitable zones because they are dim. A planet may need to orbit very near the star to get enough warmth, which also means its year can be short. Many red dwarf habitable zones are inside about 0.2 astronomical units, an orbit closer than Mercury's, and that closeness changes how winds and flares interact with the planet. It's a gentle reminder that habitable is not one simple condition, it's a whole environment. And for one sleepy soul, that's enough to rest. Young stars can flare, which matters for nearby planet. Flares send bursts of radiation and particles, and over long time they can influence atmospheres, especially for worlds that orbit close. Some flares on active stars can exceed typical solar flare energies by orders of magnitude, though the details vary widely from star to star. Stellar winds can erode planetary atmospheres if protection is weak. A planet's gravity and magnetic field help hold on to gas, and if either is too small, the wind can slowly strip atmosphere away. The comparison is simple. If particles moving past a planet can exceed the planet's ability to keep gas bound, then escape becomes more likely. The Sun's early years were likely more active than today. Young stars often rotate faster, build stronger magnetic fields, and show more frequent outbursts and then calm down gradually. The decline happens over billions of years, which means the Sun's quiet stability is something it grew into over deep time. It's not a switch, but a long easing. If you drift a little, stellar metallicity helps predict how likely a star is to host giant planets. More heavy elements mean more solid material to build large cores, and large cores are thought to be a key step toward forming gas giants. The correlation is statistical rather than absolute, but it's one of those calm patterns that emerges only when you compare many systems. Stars and disks exchange angular momentum, shaping rotation. Magnetic links between a star and its disk can act like a coupling, sometimes keeping the star's spin aligned with the disk's motion for a while. These interactions unfold over millions of years, a slow negotiation that sets the star's youthful rhythm. As disks thin, leftover debris can produce dusty belts. Collisions among leftover small bodies grind material into fine dust that can glow faintly in infrared, making a halo or ring around the star. Debris disks can persist for hundreds of millions of years, long after the gas-rich protoplanetary stage is gone, like the lingering dust in a room after construction has ended. Sometimes the system keeps a faint outline of its earlier shape, and for one sleepy soul, that's enough to rest. Some disks show eccentric dust clumps hinting at hidden planets. A planet's gravity can shepherd dust into arcs, piles, or brightness asymmetries, the way a moon can shape rings. The clumps can orbit over years to decades depending on distance, tracing the unseen motion of the body that may be guiding them. Star birth and planet birth overlap in time. Planets begin forming while the star is still young and sometimes active, and the disk is still present and evolving. The key window is often described as the first 1 to 10 million years, which is long enough for many slow processes to run, and short enough that the disk's disappearance matters. Most of the atoms in your body were once inside older stars. Elements like carbon and oxygen are built in stellar interiors and then spread outward by winds and explosions, mixing into future clouds. The Sun is a later generation star, enriched by earlier generations, which is why its small percentage of metals exists at all. It's a gentle continuity. Older stars quietly stock the pantry. A newborn star's environment is shaped by neighbours, not just itself. In crowded nurseries, nearby stars can heat, compress, or strip material, influencing which disks survive and which clouds collapse next. Cluster separations can be fractions of a light year, close enough that one star's light can change another's immediate surroundings. And for one sleepy soul, that's enough to rest. The spectral types, OBAF, GKM, classify stars mostly by temperature. It's a sequence that also tends to track typical mass and colour, from hot, rare blue stars down to cool, common red dwarfs. A useful anchor is that O-type stars can exceed 30,000 Kelvin at the surface, while M-type stars can be below 3,500 Kelvin, spanning a wide range of stellar warmth. And within that range, the same basic physics repeats in different tempos. O-type stars are rare, but dominate their surroundings with intense ultraviolet light. Their radiation ionizes gas and shapes whole nebulae, creating bright bubbles and sharp-edged structures. Their lifetimes are short, often under 10 million years, which means they change the neighborhood quickly and then disappear, leaving behind enriched material and reshaped clouds. Sun-like stars expand into red giants when core hydrogen runs out. Fusion continues in shells around the core, and the outer layers respond by swelling outward. The radius can grow by tens to 100 times, turning a once compact star into a vast, cooler surface that glows with a softer, redder light. The helium flash is a rapid start of helium fusion in some red giants. In a dense core where pressure doesn't respond normally to temperature at first, helium fusion can ignite quickly, though the energy is mostly absorbed internally rather than bursting outward in a dramatic way. The internal ignition can unfold over minutes to hours in the core, while the star's surface changes remain calm and gradual. It's a dramatic physics event that looks quiet from far away, which fits the way stars often behave. A small step forward, as red giants evolve, they can shed outer layers into space. Pulsations and winds help lift gas away, enriching the surrounding interstellar medium with new elements and dust. Mass loss rates can be around 10 to the power of -7 to 10 to the power of -5 solar masses per year, a slow exhale that continues for a long time. A planetary nebula is a glowing shell of gas from a dying sun-like star. The hot core left behind shines through the expanding shell, making it glow in delicate colours and filaments. The visible phase can last around 10,000 to 50,000 years, which is brief compared with a star's life, like a short luminous farewell. The remaining core becomes a white dwarf. It's supported by electron pressure, a quantum effect that resists further collapse when electrons are squeezed close together. A typical white dwarf might have about 0.6 times the Sun's mass in a volume about the size of Earth, which is a peaceful kind of compression, small, dense and steady. And for one sleepy soul, that's enough to rest. White dwarfs cool slowly over time, fading like embers. With no ongoing fusion, they simply radiate stored heat away, growing dimmer across billions of years. It's one of the quietest endings in nature, not an explosion, but a long, slow fade. Mass transfer in close binaries can change a star's fate. If two stars orbit close enough, gas can flow from one to the other when one expands, and that transfer can reshape both lives. The overflow depends on separations only a few stellar radii wide, which is close enough that a star's atmosphere can become shared territory. A Type 1 supernova can occur when a white dwarf is pushed near a critical mass. Adding mass can raise temperature and pressure until nuclear reactions run away, unbinding the star in a powerful explosion. The often quoted critical mass is around 1.4 solar masses, called the Chandrasekhar limit, and it's a number that appears because of the physics of electron pressure under extreme compression. Even here, the calm point is that a simple threshold can decide an entire ending. Massive stars fuse heavier and heavier elements in layered shells near the end. As the core changes, different fusion reactions happen in different layers, so the inside becomes stacked like an onion, one shell burning one element, another shell burning another. In the final stretch, some stages can be astonishingly brief, with silicon burning lasting only days in some models, even though the star may have spent millions of years on earlier stages. When a massive star's core collapses, it can trigger a core collapse supernova. Once the core becomes mostly iron, fusion can't provide outward support, and gravity wins in a sudden inward rush, followed by a rebound and an outward shock. The total energy involved is immense, on the order of 10 to the power of 44 joules, though much of it escapes as neutrinos rather than visible light. Supernovae create and scatter many elements heavier than iron. In the extreme conditions of collapse and explosion, nuclei can capture neutrons rapidly, building heavy elements that cannot be made by ordinary fusion in a steady core. This is one of the deep reasons gold and uranium exist at all. They are tied to rare, intense events that leave their fingerprints in the chemistry of future worlds. And for one sleepy soul, that's enough to rest. A neutron star can be the leftover core of a supernova. After the explosion, if the core is not too massive, it settles into a state where matter is packed so tightly that neutrons dominate. A common comparison is that a teaspoon of neutron star matter would weigh billions of tons on Earth, which is hard to picture, but it carries the basic message. Gravity can make matter unimaginably dense. Pulsars are spinning neutron stars that sweep beams like lighthouses. If the beam crosses Earth, we detect steady pulses, as regular as a metronome in the dark. Some pulsars spin in milliseconds, while others take seconds, so the blink can be faster than a heartbeat or slower than a calm breath. Magnetars are neutron stars with extremely strong magnetic fields. Their fields are so intense that they can stress the star's crust and occasionally release energy in bursts, though most of the time they remain distant and quiet to us. A useful number is that magnetar fields can reach around 10 to the power of 10 to 10 to the power of 11 Tesla, which is far beyond anything we encounter on Earth, and yet it exists naturally in the deep calm of space. In the background, some massive stars may collapse into black holes with little visible explosion. In some cases, the outward shock may not fully succeed, and much of the star's mass can fall inward, leaving behind a deep gravitational well and a dark, compact remnant. Stellar black holes often form with masses of a few to a few dozen suns, though the range depends on winds, metallicity, and how much material falls back. Wolf-Rayet stars are massive stars shedding outer layers rapidly. Their powerful winds peel away the star's surface, exposing hotter inner layers and filling the surrounding space with fast, enriched outflow. Wind speeds can be about 1,000 to 3,000 kilometers per second, which is swift yet steady, more like a constant gale than a single gust. Supernova remnants expand into space as glowing shells. The outward moving debris sweeps up interstellar gas, compressing it and mixing heavy elements into the wider galaxy. Over thousands of years, a remnant can grow to tens of light years across, becoming a faint ring or bubble in the starfield, like the slow echo of a brief event. And for one sleepy soul, that's enough to rest. The Crab Nebula is a famous supernova remnant with a pulsar at its centre. It shows how a remnant can remain energized from within, as the spinning neutron star pours particles and magnetic fields into the surrounding cloud. The original supernova was recorded in 1054 CE, which means this nebula is the lingering trace of an event seen by human eyes nearly 1,000 years ago. Still expanding, still glowing faintly. Stellar evolution can be traced by a star's position on the HR diagram. As a star changes, it can move across that map of brightness and temperature in ways that depend strongly on mass and composition. You don't need to memorize the paths, it's enough to feel the principle that stars leave patterns, and those patterns let us read a life story from light. Metal-poor stars tend to be older, formed before many supernova enrichments. Early gas contained fewer heavy elements, so stars born then carry a simpler chemical signature. Extremely metal-poor can mean heavy elements less than 1,000th of the Sun's level, an order of magnitude way of saying this star formed when the galaxy had not yet been richly seasoned by generations of stellar death. Here's a calm surprise. Population 1, 2 and 3 are broad categories of stars by age and composition. Population 1 stars are relatively metal-rich and often found in the disk like the Sun. Population 2 stars are older and more metal-poor, often found in the halo and globular clusters. Population 3 refers to the very first generation, which we expect from theory but have not directly confirmed in the same way. The universe is about 13.8 billion years old, so old stars can truly mean stars that formed when the cosmos itself was young. The first stars were likely very massive because early gas cooled differently. Without heavy elements and dust to help radiate heat away, early clouds may have formed larger fragments rather than many small ones. Some models suggest masses of tens to hundreds of suns, though the exact numbers are uncertain, and the gentle takeaway is that the first lights may have been bright, rare, and short-lived. Massive stars enrich galaxies quickly because they live fast and die young. Their short lives mean they return heavy elements to space within only a few million years, changing the chemistry of their neighborhoods rapidly. In that sense, they act like quick, intense mixers, stirring new ingredients into the galactic gas that will later form calmer, longer-lived stars. And for one sleepy soul, that's enough to rest. Low-mass stars enrich space more slowly, but over very long time. Their winds and late-life shedding add carbon and other elements on gentler schedules, with far fewer fireworks. A Sun-like star lives for about 10 billion years, so its contribution to the galaxy's chemistry arrives in a long, slow stream rather than a sudden burst. A star's end can seed the beginning of new stars nearby. The gas and dust released by winds and explosions cool, mix, and drift into clouds that will someday collapse again, repeating the cycle with slightly different ingredients. Recycling times in galaxies can be hundreds of millions of years, which means the galaxy's chemistry is written in slow motion. Star birth and star death are two ends of one slow, repeating cycle in galaxies. The same atoms drift through cloud, star, wind and cloud again, taking on different roles each time. In the Milky Way today, the total rate of new star formation is only a few solar masses per year, in an order of magnitude sense, which is modest for a galaxy of this size, more like a steady simmer than a rolling boil. Under a wide sky, now you can let the story soften again, just for a little while. Take one unhurried breath in through your nose and let it out slowly, as if you're setting something down. Then allow a small pause, a quiet space where nothing needs to be counted or controlled. We've moved through a wide arc, a star's steady balance, the slow manufacturing of elements, the hush of cold clouds, and the hidden work of star nurseries. We've touched the bright, brief lives of massive stars, and the long, patient lives of smaller ones, and how endings can scatter material that becomes a new beginning. If any part of it feels distant or dreamy, that's fine. These facts can drift like starlight itself, arriving gently without asking you to stay alert. Let the sky do the thinking now. The only shape you need to hold is simple. Gravity gathers, fusion steadies, winds and light reshape, and the galaxy keeps recycling its own dust. If your attention wanders, let it wander. If your eyes feel heavy, let them be heavy. And if the science becomes a soft background hum, that's exactly what it's allowed to be. And for one sleepy soul, that's enough for the rest. White dwarfs can have atmospheres made mostly of hydrogen or helium. In these compact stars, heavy elements tend to sink under intense gravity, leaving the lightest gases floating at the top. A useful comparison is that the surface gravity can be around 100,000 times Earth's, which is enough to sort atoms by weight the way a calm, invisible hand sorts sand from dust. Sometimes it's quietly amazing that even in a star's afterlife, order still happens. A softer detail, some white dwarfs show pollution from disrupted asteroids. If a leftover rocky body wanders too close, the white dwarf's gravity can tear it apart, feeding a thin disk of debris that eventually rains down. The clue appears in the spectrum as unexpected heavy elements that shouldn't stay on the surface for long. In scale terms, the debris can form rings within a region comparable to a solar radius, a tight, bright boundary around something no larger than Earth. Neutron stars can cool by emitting neutrinos early in their lives. Soon after formation, they can lose heat quickly through neutrino emission, because neutrinos slip out without much interaction. A common timescale for significant early cooling is around 10 to the power of 5 years, which is short for a remnant and still long compared to any human history. In a different light, some neutron stars glitch, changing spin slightly and suddenly. Inside, superfluid layers may shift, transferring angular momentum and altering the rotation rate by tiny amounts. The changes can be parts per million, like a clock hand nudging by less than you can see, yet the signal is measurable and real. There's something gentle in that idea. Even the densest objects can have small, quiet surprises. X-ray binaries can form when a neutron star or black hole pulls gas from a companion. As gas falls inward, it heats to extreme temperatures, glowing in X-rays. Inner disk regions can reach millions of Kelvin, even though the system may look calm and star-like from far away. The brightness comes from gravity converting motion into heat, and for one sleepy soul that's enough to rest. Accretion disks can convert gravity into light very efficiently. When matter spirals inward, it releases energy as it drops deeper into a gravitational well. The efficiency can be around 10% in some cases, meaning a notable fraction of the matter's rest mass energy can emerge as radiation, an astonishing number compared to most everyday processes. Still, the disk itself can be imagined as a slow, steady whirl, turning fall into glow. Gravitational waves can come from merging neutron stars or black holes. They are ripples in space-time produced by massive objects accelerating, and by the time they reach Earth, they are unbelievably faint. A common comparison is that detectors like LIGO measure distortions smaller than a proton's width across kilometre-scale arms, which is a way of saying the universe can whisper, and we can still listen. It's a calm thought that space itself can carry a message without sound. Closer in, neutron star mergers can create heavy elements in a glow called a kilonova. When two neutron stars collide, neutron-rich material can be flung outward, building heavy nuclei rapidly and radiating as it expands. Kilonova light can fade over days, much faster than a supernova's longer show, like a brief lantern that quickly dims. The heavy elements remain, drifting into the galaxy's mix. A supernova remnant's shock front can heat gas to extreme temperatures. The expanding shell slams into interstellar material, converting speed into heat and radiation. Early shock speeds can be thousands of kilometers per second, yet this remnant's growth across the sky still takes centuries and millennia. What looks like a ring is actually a moving boundary. Cosmic rays include high-speed particles accelerated by shocks like supernova remnants. Magnetic fields scatter and rescatter particles, letting them gain energy over time. Some cosmic rays reach energies far beyond anything human-made accelerators can produce, which mostly means nature has long, patient ways of building extremes. And for one sleepy soul, that's enough to rest. Not all supernovae look the same because stars die in different conditions. Some explode with hydrogen-rich outer layers, while others have lost much of their hydrogen before the end, changing the spectrum and brightness curve. Their light curves rise and fade over weeks to months, a slow glow rather than an instant flash. The variety is a reminder that supernova is a category, not one single script. Some massive stars erupt before they explode, shedding shells of gas. Later, the supernova can crash into those shells, converting motion into light and making the event brighter or longer lived. Shell radii can be billions of kilometers in scale, enormous distances that still fit inside a star's neighborhood. Even before the final collapse, some stars seem to practice letting go. In the background, a black hole's gravity can bend light, a lensing effect. Space behaves like curved glass around mass, shifting the paths of light from background stars and galaxies. In strong lensing, arcs can appear at scales of arcseconds in the sky, tiny angles that still correspond to enormous distances. The effect is gentle in appearance, a slight warping that reveals deep gravity. It can feel soothing to know that light can be guided, not only blocked. Microlensing can reveal unseen objects like planets or dim stars. When a massive object passes in front of a background star, its gravity can briefly magnify the starlight. These events can last days to months, a slow swell and fade in brightness that leaves no visible ring, just a subtle curve in time, its discovery by quiet shadow. Stellar remnants help us measure ages of star populations. White dwarfs cool at predictable rates, and a collection of them in a cluster forms a cooling sequence that acts like a clock. Using these methods, cluster ages can reach 10 billion years and beyond, which is a way of saying the faintest embers can still tell time for a galaxy. And for one sleepy soul, that's enough to rest. The Sun will end as a white dwarf, not a supernova. It simply doesn't have enough mass to collapse into a neutron star or black hole. A rough threshold for core collapse supernovae is around 8 solar masses, and the Sun is far below that. There's a gentle comfort in that ending, not a blast, but a slow transformation. A red giant phase will likely reach close to Earth's orbit scale. Models suggest the Sun's outer layers will expand greatly late in life, perhaps to around 1 astronomical unit in scale, though details depend on mass loss and complex dynamics. The number matters less than the shape of the idea. The Sun will swell, breathe outward, and reshape the inner solar system. Even that in astronomy is part of a slow schedule. Planetary nebula shapes can be sculpted by companions or magnetic effects. Many planetary nebulae are bipolar, hourglass-like, or intricately patterned rather than perfectly round. Their shapes evolve over thousands of years, which is fast for a star and slow for a person. The beauty is in how gentle forces, rotation, companions, fields, can draw structure into a fading shell. Pulsar wind nebulae can form when energetic particles stream from a pulsar into surrounding gas. The pulsar's wind can be relativistic, meaning near the speed of light, and it inflates a glowing cocoon. The nebula can stay bright because the central engine keeps feeding it, like a lantern with a hidden battery. And for one sleepy soul, that's enough to rest. The chemistry of new star clouds depends on what past stars return to space. Each generation enriches the next with dust and heavy elements, changing how easily clouds cool and how readily planets can form. In the Milky Way, the dust-to-gas ratio is around 1% in order of magnitude terms, which is small by mass and huge by consequence. Some elements in your blood were formed in supernova shockwaves. The rare end stages of stars helped create and spread many of the heavy elements that later became part of Earth and life. Heavy elements are only a tiny fraction of matter overall, yet they are the ingredients of complexity. It's a quiet continuity. The distant and the intimate share the same periodic table. The night sky holds both living stars and quiet stellar afterlives. Even when fusion ends, white dwarfs, neutron stars and black holes remain as deep footprints of what once shone. Some remnants persist for billions of years, so the galaxy is filled not only with lights, but with long-lived echoes. At an easy pace, star formation in galaxies happens mostly in cold gas lanes. Where gas density rises and cooling is efficient, clouds can gather into star-forming regions. In the Milky Way, a typical total star formation rate is on the order of 1 to 3 solar masses per year, which is modest for a galaxy this large. Steady rather than frantic. Sometimes the biggest systems do their work quietly. The Milky Way's center is crowded with stars and energetic processes. The environment is denser, more dynamic, and shaped by the presence of a supermassive black hole. The central black hole's mass is about 4 million suns, which is enormous and still only a small fraction of the galaxy's total mass. The center feels like a busy heart in a much wider, calmer body. The galaxy's disk contains younger stars, gas, and ongoing starbirth. Spiral arms are common sites of dense gas and new clusters. The disk thickness is roughly around 1,000 light-years in an order of magnitude sense, thin compared to its 100,000 light-year diameter, like a wide, flat mist. And for one sleepy soul, that's enough to rest. The galactic halo holds older stars and globular clusters. It's a more spherical region surrounding the disk, where many ancient stars wander in long orbits. The halo extends tens of thousands of light-years, a broad volume with a sparser, older feel. There's a gentle contrast between the disk's ongoing birth and the halo's long memory. Stellar streams are stretched out groups of stars from disrupted clusters or small galaxies. Gravity pulls them into long ribbons, tracing the path of something that was once more compact. Streams can span thousands of light years, yet appear as faint lines across the sky. They are the galaxy's quiet handwriting. Star formation rates change over cosmic time. The universe formed stars more actively in its earlier eras and has slowed down in many regions as gas supplies changed and galaxies evolved. A common broad marker is that star formation peaked around 10 billion years ago in order of magnitude terms, meaning the universe once burned brighter with new stars than it does now. This is a story told with many galaxies, not just one. In the background, galaxies can recycle gas through fountains driven by supernovae. Hot gas rises from the disk, cools over time, and falls back, mixing material and redistributing elements. These fountain cycles can take tens to hundreds of millions of years, long enough to be invisible moment to moment and still central to how galaxies breathe. It's soothing to imagine a galaxy inhaling and exhaling over deep time. Starbursts happen when a galaxy forms stars unusually rapidly. Collisions, inflows, or compressed gas can drive short-lived periods of intense starbirth. Starbursts can run at 10 to 100 times a galaxy's normal rate, brightening regions dramatically and then fading as the gas is used or blown out. Even then, the timing is measured in millions of years, not minutes. Galactic collisions can compress gas and ignite new star formation. When galaxies interact, gravity stirs gas, creates tides, and squeezes clouds into collapse. Major mergers take hundreds of millions of years, which is a slow dance despite the violence we sometimes imagine. From a distance, it can look like two faint spirals slowly overlapping, and for one sleepy soul, that's enough to rest. The Milky Way and Andromeda are moving toward each other. Over very long time, they are expected to interact and likely merge, reshaping both galaxies. Andromeda is about 2.5 million light-years away, and a common timescale estimate for major interaction is around 4 billion years, which is so far ahead that it belongs to geology and stars, not daily life. It's restful to remember that the universe's biggest changes take their time. Stellar ages can be estimated using rotation called gyrochronology. Many stars spin down as they age because winds carry away angular momentum, especially for sun-like stars with convective envelopes and magnetic fields. Rotation periods can grow from days to weeks as stars age. The Sun's equatorial rotation is at about 25 days. It's aging by gradual easing rather than by abrupt shift. Chemical tagging aims to identify stars born in the same cluster by shared element patterns. Siblings can carry matching chemical fingerprints even after drifting far apart. These patterns involve measuring many elements, dozens in some cases, like matching a recipe rather than a single ingredient. It's a quiet attempt to reconstruct families scattered across the Milky Way. Here's a calm surprise: the Sun's neighbourhood is called the local bubble, a region of lower density gas. It may have been carved by past supernovae, leaving a cavity around us in the interstellar medium. The bubble's size is on the order of hundreds of light years, which is a broad neighbourhood that still fits inside a small corner of the galaxy. Even our local space has a history written in empty room. The Milky Way's gas is arranged in phases: cold, warm, and hot. Hot gas can reach millions of Kelvin, warm gas sits at thousands of Kelvin, and cold molecular gas can hover near 10 Kelvin. Temperature and density determine where stars can form, because starbirth needs cold, dense pockets rather than diffuse heat. These phases overlap like layers of weather in a very thin atmosphere. Starbirth is one of the ways galaxies turn diffuse gas into lasting structure. A star is a long-lived memory of a cloud that once gathered, a record of gravity turning mist into light. Stars can outlive the clouds that made them by thousands of times, which is why the sky feels more permanent than the gas that feeds it. And for one sleepy soul, that's enough to rest. Twinkling happens because starlight passes through moving air in Earth's atmosphere. Turbulence bends light slightly, making the point of light shimmer and wobble. Planets twinkle less because they are small disks rather than pure points, so the atmosphere's distortions average out. It can be soothing to remember that twinkling is mostly air, not the star itself. Telescopes gather more light by having larger mirrors or lenses. Bigger collecting area means fainter objects become visible, because more photons are gathered and focused. Light gathering scales roughly with the square of the diameter, which is why even a modest increase in mirror size can reveal much dimmer nebulae in galaxies. It's a simple geometry that opens deep distances. Space telescopes avoid atmospheric blur and absorption. Above the air, images can be sharper, and telescopes can observe wavelengths blocked at the surface like much of the ultraviolet and parts of the infrared. It's not that Earth's atmosphere is bad, it's protective and life-giving, but for astronomy it is a soft filter that space telescopes can step beyond, and for one sleepy soul that's enough to rest. The same physics that lights the sun also lights countless stars across the galaxy. Fusion and balance repeat in many sizes and temperatures, from tiny red dwarfs to rare blue giants. The Milky Way contains roughly 100 to 400 billion stars by current estimate range, which is a number so large it becomes more like a feeling, a vast population of steady lamps. There's something deeply calming in repetition at scale, one simple process everywhere. Starbirth is still happening right now in dark clouds you can't see with your eyes. Even when the sky looks still, hidden nurseries keep forming new lights behind dust, in regions that glow better in infrared than in visible starlight. New stars form over millions of years, which means the galaxy is always quietly becoming, even if nothing appears to change from one night to the next. Now, as we come to the end of this slow drift, we can let the ideas settle like dust in still air. Starlight as time travel, cold clouds gathered in the dark, protostars warming their hidden cocoons, quiet fusion holding a star in balance, disks drawing rings and gaps, giants swelling and shedding, embers cooling into white dwarfs, remnants carrying the memory of collapse, and the Milky Way turning slowly, with its lanes of gas and its long recycling of atoms. You don't need to remember any of this. You can let it all fade into a soft background, like distant light through a thin veil. If a few images remain, an unseen nursery, a steady star, a faint ring of dust, that's enough. And if nothing remains at all, that's also fine, because rest doesn't require memory, only permission. So let your breathing stay easy, and let your thoughts do whatever they naturally do when they're allowed to slow down. The universe will keep its calm rhythms without your attention, and the night sky will keep its patient glow. Good night. And if you ever feel like returning, we can drift together through another quiet corner of science whenever it suits you.